So here we have the notes for section 6.1, estimating with finite sums. So objectives. So down here we have what's referred to as an accumulation problem. So example 1 says consider a snowstorm that starts at 3 a.m. over the first 2 hours. The rate of snowfall increases from 0 to 1.2 inches per hour. For the next 3 hours, continues to fall at 1.2 inches per hour. At 8 a.m., begins to taper off, decreasing at a steady rate until the snowfall ends at 10:30. Find the total amount of snowfall that occurs. So what we're actually going to do is we're going to look at this like a graph. So well, let's see here. So we'll call this, we'll break the graph here. So there's 3 a.m., 4 a.m., 5 a.m., 6 a.m., 7 a.m., 8 a.m., 9 a.m., 10 a.m., 11 a.m. And then we only actually have one y value, and that's the 1.2 inches per hour. So starting at 3 a.m., it's 0, and then for over the first 2 hours, that means at 5, it's up to the maximum rate of 1.2. And then for the next 3 hours, it continues to fall. So 5 to 6, 6 to 7, 7 to 8. So at 8 a.m. here would be our next point. So the snowfall is constant there. And then it begins to taper off until it stops at 10:30. So what we're actually asking to do is find the area underneath this shape. Now this is kind of a tricky shape because these two sides aren't the same steepness. However, we can break it apart into some easier shapes. So we have two triangles on the ends and a rectangle in the center. So the area for the triangle are 1/2 base height, and the area for the rectangle is just length by width. So for the far right triangle, base is 1, 2, and 1/2. So 1/2 base, and the height is how fast it's snowing, 1.2. In the middle, length by width, so 1, 2, 3, and the height is 1.2. And over in this section, 1/2, the base is 2, and the height is 1.2. So if we add up all those areas, we'll get the total accumulation. Now, it's easier to think about if you look at the rectangle in the center. If you know how fast it's snowing, 1.2 inches per hour, and the number of hours it snows, that makes sense. So 3.6 total inches of snow are going to fall in this window. Same thing for your average speed. If you know what your average speed is, and you know how long you're driving, you can figure out how far you've gone. So let's take with the calculator. So 0.5 times 2 times 1.2. So this far section over here on the left, 1.2 inches of snow will fall. In the middle, I did in my head, that was 3.6 inches. And on the far right, 0.5 times 2.5 times 1.2 is 1.5 inches of snow will fall. So 1.2 plus 3.6 plus 1.5. So all in, there'll be a total accumulation of 6.3 inches. Okay. So here we've got a little bit more generic thing. Particle starts at x equals 0 and moves along the x-axis with velocity t squared, whereas the particle at t equals 3. So we have our velocity and our time. So it's going to actually draw a lovely parabola. So 4 and then 3 be actually at 4, 5, 6, 7, 8, 9. So that's our velocity curve. So distance is velocity times time, but the thing is it has a changing velocity. So we can't just use our regular car analogy I used up here because our velocity changes. So what we're going to do is we're going to subdivide this, and we're going to use an approximation. So I'm going to just divide this into 3 sections from 0 to 1, 1 to 2, 2 to 3, and then find essentially an approximation for the velocity during those time blocks. So to make the calculations easier, I'm just going to draw rectangles, and I'm going to use the height in the center of each block. So I'm using that for my height. Oops, that was a bad example. There. and there. So this x value is actually at 0.5. This x value is 1.5. And this x value is 2.5. So for this block, we need to find the value that lies on the curve. So we need v of 0.5, which is just 0.5 squared, or 0.25. For this block, the height is the velocity at 1.5 seconds, so 1.5 squared, which is 2.25, I believe. Grab my calculator and make sure I'm doing these right. 0.5 squared is a quarter. 1.5 squared is 2 1/4. And then the last one is 2.5. So that's 2.5 squared, which is 6.25. Now each of these things have width of 1, which means the area of these rectangles is just 1 times these values. So for 1 second it travels this speed, for 1 second it travels this speed, for 1 second it travels this speed, so we just have to add them up. So 0.25 times 1 is the distance it travels in the first second, plus 2.25 times 1, the distance it travels in the second second, plus 6.25 times 1, the distance it travels in the third second. So 0.25, I should be able to do this in my head, but I already got my calculator in front of me. Well, that's not right. 0.25 plus 6.25 plus, there we go, 8.75. So it travels 8.75 units in that first second. Okay, and then so what I did there is referred to as a midpoint or rectangular approximation, where you, in each of your intervals, you find the middle height, so you choose the value out of the center. There's also something referred to as the LRAM and the RRAM that just tells you where you draw your rectangles. So for example, for LRAM, if I have my curve, the left edge of the rectangles sits on the curve. There's actually one here, but it has height 0. For RRAM, the right rectangular, your rectangles, the right corner of your rectangle sits on the curve itself. So it's just, so you can either choose, the right side, the left side, or the middle. It's your choice which one you use, unless it's specified by the question. Okay, so it says the figure below shows the graph of x squared sine x on the interval from 0 to 3. So here's our heights, 2 up to 4. Estimate the area under the curve. So I'm going to use, is this the last thing you got? Sure. Now we'll see if we can do it with all of them. We'll do 3 subdivisions. So we'll do, so for MRAM, I'm going to use 1, 2, and 3 as my things. So I need f of 0.5, f of 1.5, and f of 2.5, the midpoints of each of these intervals. And then I would total these values up. Since the widths are 1, it makes it easier. Now you can subdivide farther. The smaller you make your subdivisions, the better off you are. So 0.5 squared times the sine of 0.5. So this is about 0.12. 1.5 squared times sine 1.5. This one is 3.25. And 2.5 squared times sine 2.5 is 3.74. So all in, I'm using MRAM, 0.12 plus 3.25 plus 3.74, total area of 711. So say I wanted to use LRAM. So I'm going to use the left edges. So I did f of 0. For the first rectangle, I use the left side. F of 1 and f of 2, the left edge of the rectangle. So f of 0 is going to be 0. F of 1 is going to be 1 squared times sine 1. Well, the sine of 1 is 0.84. And then 2 squared times sine 2 is going to be 3.64. So in this case, 0.84 plus 3.64, this gives me an area of 4.48. So let's try RRAM. So let's use the right edge. So f of 1, f of 2, f of 3. Well, I know f of 1 already, and f of 2, so I just calculated them up here. But I do need to figure out what f of 3 is. So that'd be 3 squared times sine 3. Hopefully I'm in radians. Okay, yeah. So this is 1.27. So adding all of these up, 0.84 plus 3.64 plus 1.27. So you get 5.75. So notice none of them are very close. Now, if I had done more subdivisions, like if I had split each of the intervals in half, so I'd have an interval from 0 to 0.5, 0.5 to 1, 1 to 1.5, 1.5 to 2, 2 to 2.5, 2.5 to 3. The smaller my subdivisions get, the closer these values will actually come to each other and the actual true value. These are approximation methods, it's right up here in the name. Approximation methods. They are not the actual values, which is why they vary so much. Depending on where you choose your intervals, you get different values. But that's a rough way to do it, which does in fact bring us to the end of the section.